Alright, I just finished recording another video where halfway through I realized there was a step that I didn't understand. So I had to quit. Hopefully that doesn't happen this time. I don't think it'll happen, but no guarantees. So, anyways, we have W is an irreducible two-dimensional representation of S4. You haven't seen this lecture notes, or you probably have. I don't know how you would, unless you've taken the class. You probably haven't. So, everything that you need to know about this will be in here. And I don't have the character table for S4 with me, but I don't think they're maybe this will determine it uniquely. It might not. I forget. But anyways, it's going to be the character that has this decomposition, 202 negative 10. So yeah, it's that one. So anyways, let's induce it to S5 and see what happens. And right as a direct sum of irreducible representations. Alright, so basically what we do, the first thing is we count the number of things in the conjugacy classes. This is based on a previous exercise, or this is small. S4 is small enough you could easily do this by hand. Count it in your head. So let W be that thing that we were talking about, and this is its character table. Well, no, this is what the character is evaluated at on the conjugacy classes. So this is what the character is. Anyways, we can write the induced as a direct sum of VI's, and each VI is repeated with some multiplicity MI, and the VI's are non-isomorphic irreducible subrepresentations of W, and their multiplicities, of course, are MI. Then, by Frobenius reciprocity, we can compute the multiplicity by, this is going to be this, well, is this MI, or is this... We know that this is MI. This is the number of times that that the representation I appears as a subrepresentation of this induced representation is just given by this inner product. But by Frobenius reciprocity, this induced on this side becomes the restriction on this side. And how do we find the restrictions here? We just look at the character table for S5 and then just remove the rows remove the columns that correspond to conjugacy classes which cannot appear in S4. So if you look at elements of, for example, you look at elements of the form 1, 2, 3, 4, basically products of two cycles. Sure, there are examples of these types of things in S5 which are not contained in S4, obviously, such as if you had 1, 2, 4, 5. Obviously, this is not contained in S4. Well, I mean, we're thinking of S4 as permuting the indices 1 through 4, and since this has a 5 in it, this is contained in S5 but not S4. But there are things of this type which live in S4, such as this thing. So we keep the column. We just have to adjust the number of elements of the conjugacy class to whatever we have in S4. But anyways, so there were the ones we had to cut out were the ones that could only be viewed as things in S5. So there's that. But anyways, on the left here, so basically what I've done is I've copied and pasted the character table of S5, which we computed in the previous exercise, which is the one that I messed up on, so it's probably not... It might be uploaded at some point in the future. But if you don't have the character table for S5, basically you could always just look it up if you wanted to. And just looking at these first two columns here, they uniquely determine it. So if you look up a character table for S5 and you look up whatever names they're referred to as in whatever reference you're looking for, you can just match them up to here. These chi1, chi-sine, chi-v2, v2 sine, w3. Basically, sine is what you would expect. It corresponds to viewing the sine group homomorphism as a representation. V2, W3, and 7, these are just things that came up in the proof of, or in the computation of the character table for S5. So these are not like standard names or anything. I'm trying to be consistent with the notation that I used previously. But you don't really need to know what these are. All you need to know is the character tables. So anyways, this is what we have. So from here, we just need to compute multiplicities and find things which are contained in this induced representation. Now, let's see here. Let's just relabel these now, because this is a lot to write down. I'll just call this Chi1, Chi2, Chi3, Chi4, Chi5, Chi6, and Chi7. Not, which is abusive notation, because we've already got a Chi7 here. Luckily, we don't use it again, so that's fine. And the underlying vector spaces will be W1 through W7. Again, that's abusive notation, because we've already got a W3 here. Don't worry about it. Anyways, so what's the dimension of this induced representation? Well, we've proven the formula for this. It's the dimension of the thing we're inducing times the index of the subgroup. So S5 has order 120, and S4 has order 4 factorial, which is 24. And you divide that, you're going to get 5. And then W, we said already has dimension 2, and so it's 5 times 2, which is 10. So we need the dimensions of the VI's, the sub-representations of this induced representation, to add up to 10. So let's compute the multiplicities of these chi-i's in multiplicities of the wi's in the induced thing. Have we given a name to the induced thing? I don't want to have to refer to that. I'm just going to call it induced. Anyways, so for these, basically we're just going to compute this inner product. And what you do there is you take, for each of these things, you sum over the order of the group, and then you take chi W sigma inverse times chi, and then whatever thing we're taking here, sigma. Now, chi, I discussed this in the previous problem. Again, I may not upload it, but sigma, chi sigma inverse is going to be chi sigma, because in this scenario, well, it's not equal to that, but yeah, chi W sigma inverse is equal to chi W sigma, because conjugacy classes in permutation groups contain their inverses, because inverses preserve cycle types. So anyways, what we do is, for each element in S4 in a particular conjugacy class, the character is going to be constant, so you just multiply the number of things in that conjugacy class times, well, the one character we're looking at times the other. So for here, if we look at the first conjugacy class, it contains just one element, and then we multiply what chi W sigma is on there, or sigma inverse, which is the same as sigma. And W up here we get 2, so that's where this 2 comes from, and then here, chi 5 of sigma, we look up here, 1, 2, 3, 4, 5, so this one, you get a 5. So 5, and then you just go through the rest of them, you get this, and you get this, and you just add them up, you get 1. So W5 is a 5-dimensionally irreducible subrepresentation of this induced representation. Now let's look at chi 5 and chi 6. Chi 5, so these two, where do they differ? They differ on this one corresponding to 1, 2, and on this one corresponding to 1, 2, 3, 4. But look here, at 1, 2, chi W is 0, and chi, the one containing 1, 2, 3, 4, is also 0. So when we compute the inner product, it's going to, it doesn't take into account these two columns. And so the computation is going to be completely identical, because all the numbers are the same, because all the numbers that actually matter in the computation for these two are the same. We get the 5s, the 1s, and the negative 1s. So here, like this 5, this 1, and this negative 1. It'll be this exact same computation, and so therefore the inner product of chi W with chi 6 is 1. So then W6 is, let's see here, 5-dimensional subrepresentation of the induced. So let's see here. So now, what's the dimension of, if we stop here, the dimension of this direct sum is just you add up the dimensions, and that's 5 plus 5, which is 10, which is the dimension of the induced representation. So it has to be that the induced representation is equal to these two. Basically, by looking at the dimensions, we see that there's no more room to have any other additional have any more subrepresentations of this induced representation. Alright? So, therefore, we have written this induced representation as a direct sum of irreducible representations of S5. More explicitly, we've written it as the direct sum of W5 and W6. And therefore, we have completed the exercise.